Alright, I'm going to find out something about you guys, at least maybe about some of you, who recognizes these dice. Yeah, Dungeons and Dragons dice. Alright, cool. Any case, these are certainly some special dice, not your typical ones at all, but we're going to work with probabilities and calculating probabilities. In order to discuss these, I got to build up a little bit of vocabulary in you. So let's follow along with our PowerPoints. By talking about an event. So we're going to be conducting experiments that are going to produce certain outcomes. An event is a collection of those outcomes. So if I'm rolling dice, that could be the experiment, and the outcome would be the numbers that turn up on the dice. Simple events are events that can't be broken down any farther. So one of the things I have with me up here is a 20-sided dice. Trying to remember, I think the fancy word for this is an icosahedron if you want to impress your buddies on Words with Friends. But 20-sided dice. Now, an event, a simple event is the number 1, rolling a number 1 or whatever number that rolls up with. But more generally, an event could be rolling an even number or an odd number or rolling a 1 through 10, etc. So it kind of depends on what you define it as. But an event is any collection of outcomes in your experiment. Now, the whole collection of outcomes is what's called your sample space. Everything that can happen, that's called your sample space. Now, that can be kind of simple or complex depending on the example. So if you're tossing a coin, your sample space is pretty simple. It's heads or tails. All right, there's nothing in between. And the events would be a head or a tail. Typically, we talk about the probabilities of an event by letting a letter denote the event, A, B, or C, or whatever letter you want to choose. And then we'll talk about the probability of A. Now, there's a few rules that we can use to calculate probabilities. The basic one and the most intuitive one is this one here. The relative frequency approach. You look at how often something occurs, and then you divide by the number of times that a trial was repeated. So that's kind of a way to feel your way up to probabilities. Let's flip over to this one real quick here. There we go. Let's discuss some probabilities. So with respect to this one, what's the probability that Binkley's going to get paid? Yeah, 1 out of 2, 50%, right? All right, feel free to laugh. Remember, we're mic'd up. All right, good. Thank you. So 50%, it's 1 out of 2. So you're looking at the number of things that can happen, which is 2, and the number of ways you can meet with success, which is a 1. So that's actually calculating things as opposed to a relative frequency approach. It used to be before pioneers like, I think his name was Blaise Pascal, actually spent some time with probability. It used to be that people would experiment again and again and again to try and figure out what the probabilities would be. But the more determined approach is to find the number of ways that an event can occur and divide it by the number of simple events, what we just did. Now, there's subjective probabilities. There's a way to get at these as well. Let me kind of fast forward a little bit down here and talk about some of the extremes. When you're talking about probabilities, this kind of reflects back to this one right here. The number of ways that something can occur divided by the number of possible or number of different simple events. This kind of puts a limit on the values you can get. The smallest number that you can have in the numerator would be 0, in which case the probability of the event would be 0. And that's associated with something that's impossible. On the other hand, there's something that's guaranteed to occur, a probability of 1. and it can't be anything outside that. Probabilities are strictly between 0 and 1. Or if you turn them into percentages, they're strictly between 0% and 100%. You can't have a 110% chance of rain tomorrow. It's just the maximum is 100%, period. So let me then back up now to subjective probabilities. You can't always kind of sit and count the number of ways that something can occur and then divide it by the total number of things in the sample space. Sometimes you kind of hem and haw at it and give it your best guess. So let's give something our best guess. Let's let A be the event. The Lions win the Super Bowl. Yeah, and you can come up with your own probability of that event. What kind of values do most of you think? Probability that the Lions will eventually win the Super Bowl? 5%? Yeah, I think you're probably on the generous side, but that's good. Glass is half full, right? All right, I'd probably give it something with maybe a few more zeros, but you know, it's a subjective probability. So we just don't know. You can't really figure out this one by some means of calculation. All right, so let's go back. Let's go back and discuss a few more of these things. How about the other extreme? Can somebody give me something that has a probability of 1? There's two things that usually are said together that have a probability of 1. Does anyone know what those two things are? Chuck, you got to know this one. Death and taxes. There you go. Death and taxes. Probability of 1. And taxes. Hard to say which one's worse. All right. But there's other things that are kind of guaranteed to happen. So those that have probabilities of 1. And then you have everything that's in between, different certainties. So something that's likely is going to be closer to a 1. Something that's unlikely is going to have a probability closer to 0. Let's take a look at a couple of those on that spectrum. Problem number 10. So let me switch back to the screen here. Assume that 400 births are randomly selected. Use subjective judgment to determine whether the given outcome is unlikely and also determine whether it is unusual in the sense that the result is far away from what is typically expected. So, suppose you're checking up birth certificates and you randomly select 400 somehow and you found that exactly 380 of them would be girls. Is that unusual? Is it unlikely? Yeah, I think it'd be really, really a lot unusual. What would you expect if you had 400 birth certificates and you're looking at the gender? What would you expect, roughly? Yeah, about 200, about half of them. So to get something so far away from that would be extremely unlikely. In fact, the instructor calculated the odds here, and I have to express this in scientific notation so that we can actually get out of here today. It'd be 1.097 times 10 to the negative 87th power. So it'd be like 86 zeros, and then you start writing your probability. Basically, it's about the probability of the Lions winning the Super Bowl, right? All right. So how about the probability of getting exactly 197 girls? Is that unlikely? It's not atypical. I mean, it's not necessarily likely, but it's not atypical. The actual probability here is about 0.038 or 3.8%. So yeah, that's not unusual to get exactly 197 girls in that sense. So, okay, let's actually do some calculations then. A little history quiz here for you. So, I'm sure you've run into this. There's a multiple choice question on a test. Who was the 14th president of the United States? Taylor, Fillmore, Pierce, or Buchanan? Now, if you had to make a random guess, what are your chances of success? Yeah, 25%. All right, time for you guys to show off your history. Who was the 25th president, or who was the 14th president of the United States? Pierce. Yeah, Pierce. Good job. How many people knew that? All right, really? Wow, I'm impressed. Good job. You saw me looking it up? Because I didn't know either. I had to look. I'm like, I don't know. So I Googled it while you guys are on break. All right. So a 1 in 4 chance, though, is what we're looking for. That's what we're after. Let's do a couple more here. This is express the indicated degree of likelihood as a probability value. So between 0 and 1. This is while this exercise is being created, the author, weather.com indicated that there was a 20% chance of rain for the author's home region. So what's the probability of rain then? 0.2. See, this is a kinder, gentler math class. 0.2, that's it. When rolling a pair of dice at the Bellagio Casino in Vegas. Ooh, I'll be there this summer. Yes. Yeah. When rolling a pair of dice, there's a 1 in 36 chance that the outcome is a 12. Well, not with these dice, but. So, a 1 in 36 chance, well, 1 divided by 36 is going to be about 0.0278, or about 2.78%. So, kind of unlikely. And just so that you don't sound like a rookie when you hit the tables, if you ever go to the casino, rolling a pair of ones would be called snake eyes. So, sound like a pro when you go out there. Let's look at some other ones. And this is all going to go back to a table that's on page 133. So let me copy the results of that table down here for you. And then we'll talk about that table. So there's our table 4.1. So what they're doing is they're asking, this table regards pre-employment drug screening results. Now, somehow or another, we actually know the truth about these. Subject uses drugs and subject doesn't use drugs. Subject doesn't use. And then you have a positive test result and a negative test result. Positive test and negative test. And let's look through at a few of these. There was 44 people who used it and tested positive. There was 6 that used it and tested negative. There was 90 who tested positive but didn't use it. And there was 860 who didn't use it and tested negative. So if we add things up, we get 134 that tested positive and 866 that tested negative. 50 that actually used it and 950 that didn't, for a total of 1,000. Thank you. So let's try and understand this a little bit better. If somebody used it and tested positive, Well, that's a correct result, right? Where's the other correct result in this table? Yeah, the negative and didn't use it. So these are the correct results. So let's put that in here. Correct result. What's happening to these poor souls? Those would be a false positive. So, no wait, no, these are false negatives, right? They got lucky. Whew. They're breathing a sigh of relief, man. Yeah. So those are false negatives. And last but not least, we have false positives. These are people going, hey, wait a minute. We got to do that again. So let's see. Here we go. False negatives. So let's answer a couple questions with regards to this. So you've got 1,000 people here, and it asks for you to find the probability in problem number 22 of selecting someone who got a result that is false positive. Who would suffer from a false positive and why? So let's see what notation you want to use. Let's just use FP for a false positive. So we could ask for the probability of a false positive. Well, that probability is just a ratio. What ratio should I use here? Well, let's start out with how many subjects were tested altogether. There was 1,000 of them. So 1,000 of them in our experiment. How many of them are false positives? You know, I wrote false negatives here. Should it be a false positive? Yeah, there we go. False positive. Yeah, false positive. There we go. Never happened. False positive. So it's going to be 90 over 1,000, or about 0.09. 9%. So the follow-up question was, who would suffer from a false positive result? Yeah, the 9%. The applicants, right? It's the people who are applying whose result came back positive, even though they don't use any drugs. So it'd be the applicants. Let's switch over to the second one in this series that we're going to do. That is problem number 24. Find the probability of selecting someone who does not use drugs. So, again, we'll come up with a name for an event. Doesn't use drugs. I don't know. Anyone want to come up with a letter? We just D. All right. Probability of D. Try and figure out what you think is that probability. Let me zoom out a little bit there for you so you can see all this. What should I put in the numerator? Yeah, 950. So about a 95% chance, or probability of 0.95, of getting somebody who doesn't actually use drugs. Okay, these kind of tables are pretty nice to work from. You can ask other questions. What's the probability of a correct result? Let's just go one more beyond what the book's doing for us. What's the probability that this test gives a correct result? One more time. Good. There's 44 plus 860. There's 904 different correct results out of the 1,000 people tested. So what do you think? Is this test pretty good or no? There's a lot of these people here. A 9% chance of a false positive? Yeah, that's not too good. That's actually a problem for researchers, is coming up with a good test so you don't have too many false positives and too many false negatives. There was a big brouhaha a few years ago about making getting screened for breast cancer public policy or not, and part of it I think had to do with the false positives and getting people upset because they got a positive result from this test, so they need further testing. So that was part of the controversy. I'm not going to get into all of it, but that was certainly part of it. Okay, let's move on to problem number 28. So there was a 19th century geneticist, Gregory Mendel, who did a lot of famous experiments with peas to try and figure out some stuff about genetics and how things blend, etc. And so one sample of offspring consisted of 428 green peas and 152 yellow peas. Based on those results, estimate the probability of getting an offspring pea that is green. Is the result reasonably close to the expected value of 3/4 as claimed by Mendel? So, well, going back to our notion of probability, what we have to calculate is the number of possible ways that an event can occur divided by the total number of different sample events. So we need two things. We need the numerator and denominator. So let me switch back here. Let's work on the denominator first. How many possible events are there, or how would you calculate the number of possible events for this experiment? Perfect. You have to add up the total of green peas and yellow peas. Find out how many peas are there in this experiment. And then what's going to go in the numerator? Good, the 428. So let's write that down. Problem 28. It's going to be 428 divided by 428 plus, what was it, 160, 152. Thank you. Plus 152. So 428 divided by 580. It should be around 73%, I'm thinking. Let's do 42 divided by 580. Thank you. 73 point, if you multiply that by 100, make it easier. 73.8%. About 73.8%. So is that close to the actual true value that Mendel predicted? Yeah, it's pretty good. In fact, people have done a lot of work with Mendel's data and found that it was too close, that it seems like his results were rigged. And they don't blame Mendel himself. They blame his assistant. They think that the assistant knew what he was expecting and helped rig the results. But his results from all his experiments are just a little bit too good to be believable. In fact, I think they've concluded that, they were faked. All right. One last problem from this section. Problem number 30. Credit card purchases. In a survey, 169 respondents said they never use a credit card. 1,227 say they use it sometimes, and 2,834 say they use it frequently. What is the probability that a randomly selected person uses a credit card frequently? Is it unlikely for someone to use a credit card frequently? How are all these results affected by the fact the responses were obtained by those who decided to respond to the survey posted on the internet by America Online? So let's handle them one at a time. In fact, I want you to handle the first one. Calculate the probability that somebody selected at random uses a credit card frequently. So this first one's up to you, and then we'll discuss the next one. So at home, if you're watching this, and you see this little pause sticker here, you can kind of fast forward until I move it. That's when I'll start talking again, at least on the video. Okay, so the big thing to do to find the denominator is add up all those numbers in the denominator, the never used, and then the various degrees of other use. Now, which one of these do we want in the numerator? 2,834. Good. So we add that up. 2834 divided by 169 plus 1227 plus 2834 should get about 67%. Very, very close to 67%. So 0.66997, about 67%. And when you do a problem on the test for me, I'll be very clear about where I want your decimals rounded to. But in this case, 67% seems like a good place to cut it off. Okay. You know what? There is a little bit more I want to do here in this section, and it has to deal with odds. So let's move over to problem number 44. The roulette wheel has 38 slots. So you got 36 numbers, and then a 0, and then a double 0. So that's what you're going to find on a roulette wheel. If you place a bet on an outcome, if your outcome is that you're going to turn up an odd number, let's figure out the probability of actually winning. So, problem 44. Odd numbers. How many odd numbers are there going to be between 1 and 36? 18. And then even numbers. Between 1 and 36, again, there's going to be 18. And then there's 0 and double 0. And that's going to account for the total of 38 possible events in the sample space. So when you roll that roulette wheel, one of 38 things is going to happen. What's your probability of an odd number occurring? What's the probability that of those 38 events, you roll an odd number? Okay, sounds pretty good. And what did you do to get that probability? What was the numerator? Good. 18 divided by 38. So that's your chance of winning if you're going to bet that the outcome is going to be odd. Now, to ask you for the actual odds against winning. So the odds against would look like this. It'd be the number of ways to fail, colon, the number of ways to succeed or to win. So in this case, the number of ways that you can roll an odd number would be 18. What are the number of ways that you could fail to roll an odd number? 20. If you put this in lowest terms, it would be equivalent to 10 to 9. So there's 10 ways to lose for every 9 ways there are to win. So those are the odds against winning. Now, so when you bet that the outcome was an odd number, the payoff odds are 1 to 1. So how much profit do you make if you bet $18 and win? So payoff be 1 to 1. So if I bet $18, so this is what you bet, and this is what you win. If you bet $18, what are you going to win? 18. And I love the author's cautionary note on this. He goes, how much profit would you make on a bet if you could somehow convince the casino to change the payoff odds so that they are the same as the actual odds against winning? Cautionary note. Don't actually try to convince the casino or any casino this. Their sense of humor is remarkably absent when it comes to things of this sort. All right. So if you bet $18, then you should win 20. So that difference between what they actually pay you and what they should is the house's advantage on you. It's called the vigorish. And if you're smart, then what you do is you make bets that keep that vigorish really, really small. So if you're going to go gamble, do a little research. Try and find out where you can get the odds as close to even as possible. And as the best that I know, and I'm not trying to advocate for you guys to go spend money at the casino, although that probably helps our state's education fund somehow. If you play your bets right in the game of craps, you can get the house's advantage, the vigorish, down to less than 0.5%. That's pretty good. In roulette, the house's advantage is more like 5.5%, somewhere around there. So that means on average, if you're betting $1 every time, if you bet $100, you're going to come back with $94.50. That's the house's advantage. That's why they can afford all those bright lights and stuff like that in the casinos, because they make a lot of money. Okay. Let's do one last one here, like this. Basically what you're going to do is you're going to reverse engineer things. We're going to find the probability based on the odds. So it says if the odds against an event are A to B, then the probability B over A plus B, well, this is the probability of that event. Because find the probability of the horse Make Music for Me winning the 136 Kentucky Derby, given that the actual odds against his winning were 36 to 1. So let's see what we can do with that one. So 36 to 1, that's your A to B. So A to B. If I want to find the probability that he wins, probability of winning, that would be B divided by A plus B. So what's going to go in the numerator? A 1, yeah, over 37. So 1 over 37, that's the chance that Make Music for Me would win. I don't, that name doesn't sound familiar or not. I don't really follow the Derby much, but I don't know, does anyone know if he won? No. Does it look likely? Does the betting favor him winning? Does it people? No. So yeah, it doesn't look like people think he's really got a chance. For homework, he came in 4th place. Okay, not too bad. Not too bad. So thanks for that. Let's try problems 1 through 31 and 43 and 45.